All right, my name is Ryan Sciampacone, and holy smokes, have I gotten shorter, or has this podium gotten taller? Can you see me at the back there? Yeah, good, okay. I work at IBM. I work at the Java Technology Center on the JVM, along with Dan, who's giving a talk tomorrow. And today, I'm going to talk about packed objects. Legal. This actually says, I think one of the sentences basically says, in the event of my capture, IBM will disavow all knowledge of my existence. Literally, if you read it, that's pretty much what it says. All right, the problem. So, what problem? What's the background? What am I trying to solve, or what are we trying to solve? And, what's the motivation, and what kind of conclusions have we come to so far? Well, this starts a long time ago. As IBM, we have a lot of legacy systems. We have customers with a lot of legacy systems. And so interop with Java tends to be pretty important in terms of the speed, performance, footprint, and so on. And, one of the things that comes up all the time is, okay, well, we want to rewrite things in Java. We want things to, be, rapid prototyping. We don't want to be able to have to force people to continue to operate in these legacy systems. We want to be able to upgrade, but still keep things around. And we show them Java and they're all happy, and then they think, oh God, JNI, this is just horrid, right, for interop. So that was the number one thing. And this has everything to do, this is a combination of foreign function calls. This is things like accessing data from the native side in your Java heap and so on. So all these things can end up looking horrid, and the interop aspects basically suck. And that was the number one thing. We're like, look, we got to figure out a way to be able to get past these problems. And further, if you look at some of the things that are going on today, and especially with FPGAs and GPUs and so on, being able to get your data in and out of the heap fairly quickly is hugely important. On the other side, one of the things, something that led on from that discussion was, things like locality, memory placement, and so on. These things actually ended up turning out to be fairly important for us as well, and important to everybody else. Locality in Java can matter, right? You look at JEP 142, for example, at contended. This is an important one. And the existing data placement story is actually really poor in Java. You allocate two things, you think it's in a row, you think it's side by side in the heap, it is not. You allocate something and you place the fields in an object source-wise, side by side. You're not necessarily guaranteed, that the fields are even side by side, even though you've listed them that way in the source file. And in fact, you're not even guaranteed that the fields are side by side or even in the same kind of general position when we're talking about subclass and superclass. You can get fields migrated up and down the chain based on how your data is organized. So all these things end up getting in the way. You have no control over this. That's okay for a lot of people, but in many cases it's not for a select few. And these two sort of seemingly unrelated problems are what led us down the path of packed objects. So we want to be able to come up with something that really helps us solve these problems. So let me take you through a little bit of a kind of a picture tour of what packed objects actually are. I'm going to put this here. It's going to be a disaster. All right. So going back to the native discussion, the first thing that we actually wanted was to be able to say, look, why can we not naturally refer to a native array from Java, right? It'd be really nice if we could just say, look, here's an array of int in our Java object, and be able to say, here's the storage over here. Now, there's a really good reason, of course, why you don't want to do this. You got an unmanaged pointer, problems left and right. What if somebody frees it and so on? But still, there's plenty of people that actually say, look, we really just want to be able to do that. And we don't want to have to access it through JNI or anything like that. We just want to be able to say, this array at 4, get me that integer at that position. So this is what we were basically after. And this is what a lot of people that come to us from a non-managed runtime space say, why can't we do this? We know what we're doing, we can manage it, let us do this. So, pardon me?
Famous last words.
Sure, America, I don't disagree, but there is a select group of people that actually want to do it, right? We allow people to use unsafe and direct byte buffer and stuff like that, so. But yeah, I agree. The other side is that everything's an object, and in Java, everything is an object. This is kind of a problem. If you were to sort of create kind of a very simple hash structure, This is sort of the basic layout that you would use. You'd have a hash, you'd have an array, a bunch of entry objects, key value. Pretty simple stuff, pretty obvious. But there's the usual problems associated with something like this. The first is that you've got memory bloat, right? Everything's got a header, waste of space, more frequent garbage collects, locality, and so on. I'll get to locality again in a second. The next one is, of course, pointer chasing, right? You don't know where these objects are on the heap. It's nice to be able to draw it this way in this nice simple example, but they could be scattered to the four corners of the universe within your heap. And so locality, whenever you're chasing these pointers, it's a cost, and then being able to bring that memory in is a cost. Simple stuff, everybody knows this. And then finally, locality within the object itself. So whenever you're accessing data, you access it in that array. You're pushing a bunch of potential cache lines out, going through entries that you may not actually, for keys that you look at, and you compare and you go, no, wrong key, go to the next one, and so on. All these things flush it out. And locality isn't just in the sense of looking at these objects and saying, yeah, I'm touching everything, fine. I mean, we have locality issues, and I talked about this earlier, in the sense of hot fields for objects. I see a lot of customer code, and I can tell you see this left and right. Objects with like 100 fields, you're like, oh my God, oh, we've only got 10 million of them in a heap, and you just want to pass out right away, right? Because you're like, that telling them to change your code is just a non-starter. And then you start to do some profiles, you start to look at the code, and you notice that there's only really 2 fields of these 100 that are actually referred to all the time, and of course they're really far apart. And like I said, even if they put them side by side, it doesn't matter. Right? The JVM is just going to do random things, or seemingly, from the end user's point of view, random things to your fields. All right. So, we've got some criteria here, right? We want some on-heap, off-heap seamless reference to data, and then the seemingly unrelated goal, or possibly unrelated goal, of getting rid of headers, bringing related objects closer together. And this ends up looking a lot like C structs, right? Structures. Right, in C, right? In C, one of the great things about C, there's a lot of bad things, a lot of great things about C, is that what you type is basically what you get, depending on what the compiler wants to generate in terms of code. But when I specify something like this, this is pretty much what I get. It's a nice compact representation. There's padding where needed and so on. But we haven't got things like headers and what have you. So it's exactly what I want. Right? And I can place things according to, say, frequency of access and what have you. Right? So this is sort of the criteria that we're headed towards. All right. So let's just go over some basics. This is what packed objects looks like under the covers. So what I'm going to do is I'm going to take a variety of scenarios in terms of objects, just regular Java objects, and then sort of showing you what underneath, under the covers from a VM implementation point of view, what the equivalent packed object representation is. And then hopefully from that, I'm able to take you back to locality, native referencing, and so on, and be able to show you how that works and how, from a Java developer's point of view, ignoring the dangling pointer problem, how you can just use this like a regular old object, and it's a very natural thing to do. All right, so let's take a point. Let's take something really simple, right? A point object. You've got a header, and you've got an X and a Y coordinate. So what would that look like as a packed object to start? So base case. So what we're going to do is we're going to introduce 2 new fields, target and offset, into the object. Okay? And this will be a packed point representation. Now this isn't the same class as point. We've actually created a new type called packed point. Now the first thing you're going to say is, well, Ryan, you just talked about getting rid of headers and improving locality and memory. Then you go and you introduce 2 fields on the header of every packed object. So haven't you kind of done things backwards a bit? Go with me here, okay? We'll get around to actually shrinking this down. So what is target and offset? So whenever I'm referring to the data for a packed point, whenever I'm looking for X and Y, I have to do 2 things immediately off the packed point. The first, or rather, the data is actually going to be represented as the target will point to the actual object where X and Y are found. In this particular case, itself. Secondly, offset will point to the relative offset from the start of the object to where the data is found. So in this particular case, the base case, right, if I'm looking for X and Y for this packed point, I would follow the target pointer back to myself and then say, use the offset to find X and Y, and there will be my coordinates. Again, seems a little bit inefficient, but as we build on the examples, you'll see where this is headed. So let's take a line with 2 points. And this is, again, what it would typically look like in Java. The usual problems. In the packed representation, this is what a packed line would look like. Okay? So here again, if I'm looking at a packed line, its target will point to itself and its offset will point to the data. And of course, it's got the start point S and the end point E embedded directly in it. Now this is different than Java, standard Java objects. The data is actually embedded directly in it. So how do I access that, right? And these are actually, there's packed point S, you can see it here, right, and packed point E. You can see where the data is, but this is a much different representation underneath the covers than what you're used to. And from an expression point of view, now let me be clear here, we're runtime guys, or I'm a runtime guy. I'm not suggesting this is the syntax, I'm just saying let's just use this for now, okay? Kind of go with me on this. But this is the syntax that you would use to express it, which is actually really cool because you're not really far away from how you would just express things normally in Java, right? You don't have to go play tricks or huge syntactic differences. It looks pretty much like natural Java code. But of course, there's kind of a problem here, right? Is how do I actually access the points, right? What if I say a packed line .e, how do I get that point, right? Java programmer wants that object out. Well, here's where the magic of the secret sauce of the whole thing comes in, is you actually create really a derived object where you have a packed point. Now remember, this is under the covers. This is the JVM doing things. So it doesn't matter what the user thinks as long as he believes that he has a point to the correct data. You'll create a packed point from a VM point of view, but you won't create the body to it. You'll actually say, no, I'm going to do away with the X and Y that I normally would have, and you just get rid of this here. And I'm going to say, well, I don't contain the data. This guy actually contains the data, and the offset will be to here to get to the endpoints X and Y coordinates. Now, I could instantiate a packed point and fill in X and Y in the body. That's OK. But in this particular case, we say, why would you bother doing that? Now, this looks somewhat inefficient, but you can think about JITs, for example, that would actually take be able to take this type of thing and say, look, I know that a packed point is going to be local, so I'm not even going to bother to instantiate it. It's really kind of conceptual. You won't necessarily be facing I guess the pressure on the garbage collector that you think you might otherwise experience. I wanted to get back to the overhead of the header too. If you had an array of packed points, this is where kind of you end up amortizing the cost sort of thing. If you end up having sort of an array of packed points, arrays actually form a really fundamental part of packed objects in general. But here in particular, you can actually see where the amortized cost of target and offset and, well, the header in general ends up being spread throughout. Because if you have a huge array of packed points, you can actually just contain them, right, X, Y, over and over again. This is really important. I want you to imagine what that would look like if you had 10,000 points or 10 million points or some equivalent data, and you actually had that with every single one of those things having a header with a very small amount of payload, right? In this particular case, you've got something that you eliminate all this header cost. Whenever you're accessing something, just a second, whenever you're accessing something, you'll create this packed point. And 90-some% of the time, that's never going to hit the heap. That'll just be something that the JIT derives. It's local. You handle the data, direct pointers right into the X and Y that you need, and away you go.
Maybe you're going to get to this, but how about mutability and identity?
Question is, mutability and identity. Of course I am. Yes. Yes. The quick answer is, would you ask, mutability and identity? Yes. And no, but then I'll fill that in later, okay?
Array slices?
Pardon me?
Array slices?
I'm not going to talk about that, but we can later. It's a good question.
Yes or no?
Maybe. Yeah, there.
What about generic?
Sorry, certainly not opposed, right? It's not something that, we're still a lot of invention going on, so yeah, I'll open for discussion, absolutely. Anything else? Okay.
What about how the center interacts with generics?
I'm sorry, I didn't hear that.
Generics.
Oh, good question. Pardon me?
Joke,
yeah. I don't have a good answer for that right now. It's a good question. Remy? Yeah, you want me to go back?
Before, why the array of packet point is a packet.
Oh, that's because I can't type. An array of packed points?
No.
Yeah.
The real question is why this object is a packed object.
Oh, sorry. So you could right. So the question is, why is the array a packed array, right? So the real answer to that is you can choose to just have an array of packed points, which is the standard way of having pointers to a packed point. A packed point is just an object, okay? So I could have an array pointing to packed points. So instead of having x and y in each of the body, like basically this is index 0 of the array, this is index 1, and so on. So instead you could have a pointer to real ones with bodies. That's absolutely valid to do. This is just an object. In this particular case, we've said, well, I actually want a packed array of packed points. And so you'll get a different type of array. This is not the same type of array as saying, a packed, like new packed point, right, with a square bracket and a number. That's an array pointers to packed points. When I say pointers, I'm talking from the VM sense.
Here, it's the fact that point is a packed point, which means that you don't have pointer in your array.
No, actually, the declaration of what type of array it is will determine whether it's embedded or not. We can talk offline about that. All right. So you can see where this is headed. Let's go back to the first problem that I actually talked about, which is, look, I want to be able to access native data from Java, right? So you have a struct point xy. So these examples are simple, I admit, but kind of transform it to your particular problem space. You've got native pointer xy, native storage xy. You want to treat it as a point. How do you have that operate from Java and be transparent? Well, it's the same idea. Again, declared the same. It's just a packed point. You declare it. You can still allocate these things on the heap as packed points with payload x and y, as within the body. However, in this particular case, to access the native one, again, without the user actually having really any concept that this is off the heap, is you just say, look, the target doesn't point to an object, it's null. And the offset is an absolute pointer directly to the data, right? Again, the VM just handles it, right?
How do you deal with code evolution? I'm writing my native, it looks like you have two different declarations.
Yeah, you do. Yeah, it's a problem. I don't have a good answer for you on that one. So the question is code evolution. Like you basically got this, you redefine the same thing twice effectively.
Right. So I mean, it reminds me of something like typically a protocol buffers where you have sort of a syntax that defines these things and it automatically generates a C++ header and a Java header, and you don't have to worry about keeping multiple examples.
Well, you do. So the answer to that is you do. You have to rerun whenever you change one of them, right?
Well, yes.
So.
One, there is a canonical representation of it. You don't have to worry about keeping two.
Sure, and so you could do the same thing here. Nothing prevents you from having the canonical representation and then generating backwards, right?
Yeah, but you're not a tool.
Not yet.
We do.
There you go. Done.
I'll talk about it in the next session.
Yeah. All right, anything else? All right, so that's a basic introduction. Advantages. Do I have this backwards? No. All right, this section's called, sorry, I was editing at the last second. I'm like, oh God, did I just move sections around? This should really just be more like, okay, let's actually build something. So let's build something and see. And we kind of already did this, so I want to really kind of breeze through this section a little bit. I don't want to really spend a lot of time. It sort of illustrates a few of the weird things. And again, you'll see some syntax here that some of you might really want to throttle me about. We're not saying this is the syntax. It's just what we're using right now, or what we believe we want to use right now. So really simple, right? Character array, address, port for address, and then let's have two of them embedded inside the header. And there's the example of having native pointers, which I'll get to later, but let's stick with this one right now. So this is nice, right? In C, again, we've talked about this, nested substructures, compact, alignment, all those things are all nice and neat. So let's build it in Java. We've already done this. Holy smokes, this is terrible, or terrible for all the reasons I've talked about. Again, headers, locality, alignment. So, but let's stop for a second and actually say, well, let's look at the Java code. And I've kind of, you'll have to squint a bit because there's at least one bug in here, I think. But the point, the point here is really to sort of look at, what do you end up getting? If you write this sort of nice, natural, normal syntax for Java, here's the bytecodes you get, pretty simple, pretty obvious, and here's the resulting, JITted code. Maybe not overly optimized, but you get the idea again. So this is actually nice, right? It's simple, straightforward, pretty obvious. I would say the one thing that maybe sucks about this is, let's go through EBX to get something, and then let's go through EBX again to get something, to get an EBX again. So, you're waiting, a bunch of stalls potentially. Performance is not going to be good for you, or not great. You do this over and over again. Everybody's used to the performance of Java being a certain way. It could certainly be a lot better. All right. What if we did this with packed? So this is the thing that you might want to throttle me for. Excuse me. Yeah, same way, spot it? Yeah. Don't charge the stage, please. I'm small. Right. So this is just to sort of say, look, it's packed representation, whatever, annotations, what have you. So the point being is that this is an embedded array, right? And they're bytes. So we stick them in there. Port. Again, it's aligned. And I'll get into alignment a little bit later. So again, the Java syntax is nice, simple, straightforward. You're used to typing this, a few minor tweaks, but whatever. And you get a great result, right? Or hopefully a great result. I mean, again, the example of the header versus the actual data is maybe a bit off, but you sort of get the picture. The resulting code isn't actually that bad. Now, you need a whole bunch of smarts in your compiler, types and so on. And in fact, there's a few other things going on here. But the bytecodes end up being the same, right? You just need a whole bunch of smarts in your VM to actually be able to say, oh, geez, he's really talking about pack types here. And then you get completely different results. Sorry, you get basically the same amount of assembly, except that it is reasonably different. And the big thing, again, like I pointed out, is you're not waiting for data to arrive to use it. You're just fetching directly off of VBX. Now, you're getting, right here you get an AGI. Okay, sorry, but I'd rather experience an AGI than a bunch of stalls from cache line misses. So it's actually pretty good. It's not bad, right? You're not getting huge code bloat or anything like that. Now, in this particular case, we know the types, but you actually have to know the types here, okay? Like you do know, it's like this is a packed guy, right? You're not going to be doing checks left, right, and center for these things. All right, so let's just flip for a second. So that was actually pretty good, right? The resulting code, everything, the way you type stuff, it's all right. It's not too bad. So what about native access, right? How do we implement this normally? So what do you normally do? And I'm going to breeze through this really quickly. Please don't read this code. There's probably bugs in it. There's a mix of Java at the top and some JNI at the bottom. That's how you normally implement it, I guess, or the standard way, straightforward, CS 101. Yeah, it's coming, guys. It's coming. But the reality here is that don't look at this. What you should really just be looking at is that. Heaven forbid. I love the discussion about 128-bit today because I'm just like, may the gods forbid that we don't get a 128-bit platform because there's going to be a lot of code that's in a lot of trouble, I think. Because this is how you stash native pointers, right? This is just what you do. There's no kind of equivalent type. There's no like sort of uint type, void star type rather, for Java. JNI costs also tend to be high, right? This is no surprise, right? I mean, you look at the amount of code calling in, calling out. You talk about arrays, there's copying. Yes, there's critical and so on, but JNI serves a purpose, a lot like light beer. What's that? For what, beer or JNI? Okay. Yeah, the unsafe implementation. You shouldn't be here, first of all. Yeah, I know, right? This is what we use, is JNI. You shouldn't be here. But the other thing, too, is that you're playing the indices game, right? You actually start to really play this. And this isn't fun. I suppose you could use tools to auto-gen this stuff, but now you're left with a whole wad of goop that just doesn't look like a Java object. And conversely, the other thing, too, with the native stuff is that you can say, well, I'm OK with dealing with this. That's fine. The reality, then, is that you don't get the other aspects of being able to deal with on-heap and packed representation, right? So instead of, although you can say, well, look, I'd rather use unsafe, then, well, you're not going to get the other benefits, right? That I'm talking about on-heap, compact representation. Direct byte buffer implementation. One might argue that this is really just a wrapper on unsafe. Again, you're still playing the indices game. So yeah, bug in this chart. I don't have like the @packed representation at the top, but this is what it looks like. We've been through this before. Nice, simple, neat, concise. They are in a lot of sense a real object, so you can add functionality to these things too. It isn't just here's my my fields and away you go, and that's all you can construct, getters and setters. Real functionality actually exists on these things. There are more than a few. All right, the first one is obviously the identity crisis, right? So you've got two types pointing to the same data. I've used native here. You could even still use something like a packed line pointing to the same 2 points. You've got two different derived objects. What does a packed line, what's the equality mean here, right, for these two things? And in this particular case, when you're talking about packed data, we've tried to make, our explorations and things that we've experimented with and so on have kind of led us to really believe, and I apologize, this is at the bottom, so some of you can't see it, but the data is what really matters here in these particular cases. It isn't actually the identity, whether you're dealing with identical objects. It's the actual data that actually matters here. And so we've actually said, well, look, when you're dealing with packed types, identity doesn't mean anything. Now, yeah, I know you can basically they can end up being cast as objects. Now you're left with an identity problem where they should look like it. I don't have a good answer for you at this time. So yes, but no, right, is kind of the actual answer. So it's not great, but it is what it is.
Well, we have this problem already with box visitors.
Right. So this is not a unique problem either, right? Absolutely. Oh, sorry, my previous one, the identity crisis, or?
No, I was looking at this one.
Oh, it's because, sorry, keep yelling into the mic here, I apologize. Right, because it's native, right? The target, it's an unmanaged pointer, so null, right? Then absolute offset to get to the native part. But again, like I said, the same problem exists on the heap too, right?
What does object dot equals
That's a good question. I actually forget. Dan, do you remember the implementation for that? You're catching me off guard, John. I can't remember, but it's easy to get the answer. Yeah.
How exactly do you deal with managing, say, like deleting native objects when there's no more?
So that's up to you, right? You're dealing with this data. You've got seatbelts off, right? So the question is how do you deal with the unmanaged part when somebody, say, calls free on this data, right, or something?
I mean more, how do you tell native code to free that object when all the pointers from Java?
That again, okay. So the answer is how do you actually manage the native data, right? Like, I mean, how do you know when everybody's not referring to you anymore? Therefore, you can free it, for example, right? Right. The answer is you're dealing with seatbelts off, so you better have an agreement and a contract on both sides, right? So. Oh, no. Okay. Maybe not. All right, so maybe you could use the finalizer. I'll argue you can't, okay? And it's actually an identity problem, right? So you have to start managing things at a certain level that we weren't willing to go to. Maybe we should, and we can have that argument offline, but I'll get to that in a second. Yes. Synchronization is the other one, right? What does this even mean, right? So if you actually, now again, this is stupid, why would you synchronize, on a packed line, et cetera, but just kind of use it at, as the example. You want to synchronize on two different things. What does that actually mean? Nothing. Synchronization there's no place for synchronization here. You're not going to win at all. Finalization is, of course, a bit of a problem. Now, it's funny because I'm going to take you on a bit of a tour here. You've got a packed point that's referring to, say, the start point of a line. What happens if you stop referencing a packed line? What does that mean, right? It's like, well, can you finalize a packed line? No, you can't because you're obviously pointing to it by the target. If points had finalizers, for example, you'd have issues too. We have this sort of problem already in terms of a lot of customer code where they'll have, say, a parent-child relationship, yet the child points back to the parent. You see this all the time. Why is my object not being finalized? Because you have a pointer to it. So right away you start ending up with weird problems where you have this point and the user can't even see that they have a reference back to the packed line. How would you finalize this guy? I've already talked about this. What about the other child that should have been finalized, or so you think under normal circumstances? You can't explain that. And if you think, look, you could have these same problems in Java already, right? These problems already exist. You could just back edges and so on in your object graph. How do you do this? right? How do you do this? You can have the GC start to manage all your unmanaged pointers and make a list, and do you have to register them? I suppose you could. Like you could, right? You throw them in a list and say, all right, it's a set, right? And with account, with
I agree this is all ugly, but you have to think, you're essentially saying this problem is too much of a mess for us, so we'll let the guys who aren't good at this solve it instead.
So what I'm actually saying is that if you're actually in this space, so the thing to remember here is this. For something like Pact, I'm hoping that this is a little bit obvious. 90-some, high percentage, 90% of some Java programs are not going to use this. You don't want them to use this, right? There's so many security holes and issues and so on. Forget it. Not happening, and you're just going to blow yourself out of the water. You're going to shoot yourself in the foot, left, right, and center. But there is a small percentage that would actually be able to use this, actually be able to manage their systems, that would allow the other 90-some% to benefit. Okay, so things like hardware accelerators underneath the covers, right? We got GPU FPGA stuff going on this week, I believe. So there's things like that. So you're going to have a small percentage that actually do understand how to manage these things. They want a very slick, easy, simple to maintain interface to the native layer. But people aren't going to see that on top, right? They're just going to say, what are the results? I'm 50% faster. I'm 10x faster.
Can I come out in support of that? I hear, when I can just come out in support of that, I hear a lot of people complain, oh, these people writing native code are out of their minds. But, at Google we have a mixed environment. We have a lot of client libraries that need to be shared between C++ and C. And Java, because if you write it twice, then you've got two complete code bases to create, which is insane. So you want to write it once. What's the obvious thing to write it in if you're going to write it once? It's C++. All of a sudden, you have to deal with JNI, and you have to deal with managed pointers, and you have to deal with performance issues. And if you could write something relatively clean and relatively straightforward in C++, I think it would be a huge win for the kind of environment that I'm trying to manage anyway. And I think probably the one that the kind of people are trying to manage.
Well, the one thing I haven't talked about either, and these things like fat binaries and being a dynamic recomp of languages like C and C++, they do exist. So operating in tandem here. But one of the things about writing this all in JNI and C is that a lot of that code is not going to get recompiled. It is what it is, right? And so if you compiled, for example, on some old architecture, you're running on a modern one, you're maybe not getting the best performance. Whereas in the environment that we're talking about here, you have a JIT, and hopefully it's doing the best job for the version of the architecture that you're on at that time. So, upgrade your hardware, same Java code. You've written the majority of this in Java and not in C. You're going to see an uplift in performance as well, potentially.
Do a lot of work on the C compiler side.
Sure. And I know there's a lot of work. We have a compiler group too. I know there's a lot of work going on there too. But right now there's still a lot of people that still compile at the lowest common denominator to make sure things work. And one of the things that people, the JIT is not just about making things fast, it's about a lot of things, but one of the things is about exploiting the hardware that you're running on at that particular moment.
Does the pointer know that the container hasn't been invalidated or freed?
No.
Is there a way?
Crashing. So sarcasm aside, no. So what we do is we say, look, the contract needs to be on both sides here, okay? Yeah, it's. I'm not saying that it's not scary, but that's what it's right now for us. That's
So what's
what the
gonna
agreement is.
happen? Maybe that's gonna crash.
Basically, yeah. Now, we're going to be able to say, look, we went through this packed type, et cetera, et cetera. The crash will tell you what happened, but you're crashing, right?
If you're lucky.
If you're lucky, or you're corrupting data, right? Or you've accessed some data that you weren't supposed to, right? You've violated some security aspect. This needs to be absolutely trusted.
Yeah, but the problem with that is that, okay, you've got two types of people. The developer writing this code, and then it's the operations people who have been spoon-fed that the JVM is very safe, it doesn't crash. Okay, it slows down.
All
It may
operations
eventually
people know
crash
that's
if
not
someone-
true.
Yeah. Well, yeah, we've had what fit.
They know they're killing themselves.
Sure. So if I could actually, I'm happy to have that discussion offline.
With GNI and with unsafe and
So
whatever.
if I could just put a halt to it. So guys, if I could put a halt to that, thank you. It's an important question though, right? Look, sure, absolutely. All right, assignment, right? If you hadn't figured this one out already with derived, headers and so on pointing back in, this is another one. If I take a packed point and I assign it into a packed line, normally you would expect I now have that point, right, in the naive implementation. Well, in this particular case, we actually copy the data, right? So this goes back in some sense back to the identity issue. It just doesn't make any sense, right? I mean, you can't take this guy, assign it into here, then refetch this and say, am I identical, right? It's about the data, not about the objects. Oh yeah, and the red for the syntax, the red is supposed to mean, look, do you change this? I'm an old small talker, so this is like, hooray, it's back for Java. But I'm not suggesting this. And the only thing that we had there was, do we actually want to point out that assignment is actually different? And then it became, well, do we really want to point out now that .e or .s is actually different too? So I'm just raising this here, I guess more or less to cause an argument or whatever, but just to point out it is different, right? It is different. Field initialization, this is the last one, and again, I'm not going to say, or the last one I'm going to talk about. Big thing here though is that you're used to this. You've got a constructor, you don't have a zero argument constructor, all of a sudden you have a constructor here with these embedded things. What does this mean? Right? What do you initialize those fields to? Do you actually hammer them to zero and then something else? Does that make sense? What are you supposed to do, right? Some hacko solution, again, not syntactically completely correct or Java correct, but this is sort of like, what do? Do you end up building something along these lines? Do you have the compiler do something like this? Do you have different rules? Do you have to express it differently now? Do you create new syntax for your constructor to actually say, for my pack types, do the following? It's a good question. That's one we actually don't have a very good answer for at all. We don't know. And we'd be ready to take suggestions. Okay, what have I got here? What time is it? About 7 minutes or so?
Yeah.
Okay. All right, some more advanced stuff, which is actually just another list of challenges. I just decided to break this up with a different heading. So if you took like a binary tree, expressed it in C, right? And you said, here's a pointer to the left side and here's the right side. This is what it would probably look like. In some sense, you'd have data and so on afterwards. We don't in Java have necessarily a representation for a pointer. We do, they're called references to objects, but you can't put unmanaged types into those things. So if I had something like a binary tree node pointing to the native data structure, and I said, dot right, what's the declaration for that supposed to look like, right? I mean, I've talked about embedding things, and you'd have a binary tree, a packed binary tree, node left and right, and that would be the embedded types, but you can't do that because, it goes to infinity. So how do you actually start to represent these things? The answer is fairly obvious, but there's actually another problem associated here too. Can anybody tell me? That's a good one. Null's a good one. I won't talk about that here, but 32-bit or 64-bit, right? It's another one. Alignment's another great one. Talk about alignment comes in with 32 or 64-bit too, right? Or they're your types, quad floats, quad words and stuff like that. Alignment matters, right, for platforms. So, the answer here is obvious for us right now, we took the obvious approach for now. I'm not going to tell you that this is the right answer, but again, instead of, you need the star here, that star is just represented with an annotation. And it's funny here, I got a bullet that says restrict for security reasons. It's like this whole deck should be restricted for security reasons. But like all of a sudden it matters, right? There's a difference. Well, okay, this one's dangerous. The other thing to remember here too is that in this particular case, there's no managed pointers. Everything's unmanaged. So there's basically no GC involvement except for the derived pointers. Right, yeah. So the final point here, I did just speak about this, is that when I do actually say this now and I go down the right-hand path, I actually end up having to poof up a new object. Right. Again, that may or may not hit the heap depending on how your code's constructed and so on. Yes, so so the question is that if I have a native pointer, can I actually point to it like from a normal Java type? And one of the problems with all my examples is that they've all either been all packed or all not packed. And the answer is yes, absolutely. A Java object can point to a packed type, and then you're in the packed universe. Okay? The simplest example is if you just have an array of objects, those things can actually point to packed types, right? Because they're just objects. And I should point out one of the silly things we actually tried to do, being guys who like to play around with the internals of the VM, at one point we actually experimented with packed types being not under the object hierarchy. Just experimented, and let me assure you that was extremely brief because it basically broke everything that we wanted to do. And you can imagine why. Like if you actually stop and think about it, it was like, why did we even try? Yeah, alignment. So, if I express this is what I would want personally, but not everybody wants this, right? The other way to actually express this is this way, or rather, the other way to format it is this way. It's actually kind of cool. I went and saved a slot. This could maybe, you could benefit from this over time, but yes, accessing unaligned, values, performance issues, you might even crash depending on your platform. I get it, but some people actually might want something like this. So either way, though, the point is that there's two things here. What's the default? And it doesn't matter because you still have to allow the other way to be expressed as well. So again, pretty simple stuff for us right now. You could pick two different ways of doing things. One is to just manually insert your own padding and just say, look, I'll handle this. But again, we sort of talked about this a bit earlier. What do you do for 32 versus 64-bit? The other thing too is it doesn't look very natural for nested types. Like, what are you going to do? Put an address here and then put some short padding thing in between? Doesn't make any sense. So just use annotations. Yeah, you'll have to express that one fairly differently. So since it's coming from one end to the other, if you have a, say, from a C, so the question is, what do you do from the C side, right? If you're trying to do this sort of like ultra packed representation, right? I might actually, just to not go down that road, but I might actually shift a little bit and say, look, sometimes you get data payloads that are actually undefined kind of thing. There isn't a C structure for it. Like you might take, say, packets of some data or something like that that just arrive. You don't necessarily have C definitions for them. And you may not need them because you don't actually have the C libraries on your side to handle it. You just suddenly get the data and you've got to consume it from Java, in which case you can do whatever you want from an alignment point of view. Yeah, I mean, it's data that you have right there. Treat it however you want, right? And Endian, of course, right? So who read Deep Cafe versus Fika? I won't even try to read it. But, and that goes back to my point of you can have a data stream of some type that's like, it's little Endian, and you're on a big Endian platform. Well, fetching your int, there's going to be a difference, right? You don't fetch an int, well, you fetch, kind of a bigger little Endian int. Again, things you have to think about. All right, in the 2 minutes I have left, let me just take you on a little bit of a tour. And that what I just talked about sort of hints at this. So use your imaginations a bit, like you haven't already with this talk, I bet. All right, so you want to move some data, and you've got like a very simple data structure, or some complex one, sitting around in your heap, and you actually want to move this over the wire to some other machine. And let's say you got some high-speed thing like InfiniBand where you can just pick up the memory and say go, and it's there in a flash. So the standard way that you might do things here is you get an array, you'd allocate it on the heap maybe. You take the data and then you move it across. You start to copy it and you do some translation level stuff maybe to sort of cram it in there. And you've got it in the array and then away you go. But that sucks, right? Why do you want to do that? You're taking your data and you're basically duplicating it to be able to send it over the wire. It's not great. So instead, let's start over again and let's go with packed. So if you took this data structure and let's assume that it wasn't something like a binary tree or something like that, and that you could represent it this way, this would be great, right? All the data's in one contiguous chunk. Just pick that chunk of data and squirt it over the wire. Done deal. Still a problem, right? What if you have two of them? Not guaranteed to be side by side. And then you start to get into this recursive problem. You can't start expressing packed as packed as packed, till the end. It doesn't make any sense. So let's start over. Region-based technology is certainly not anything new. So let's take a specialized area of the heap, and let's actually just start to allocate the packed types right into the specialized area so they're all end-to-end. We know where they are. They're all the same size because they're packed types. So it's actually very easy to manage this from a GC point of view, right? It's really just cell-based allocation and deletion. And let's just pour them in there and transmit it. That's pretty good. Still left with headers. Remember, packed types still have headers on the heap. Okay, last try. Start over again. Managed part of the heap, that's okay. Stick the packed data into the specialized heap area. Okay, end to end, no headers, everything's in there. And then actually just use the bodiless form of packed types. Now I have it pointing from target, but the implementation to be determined. But this is something that would be completely natural. And then when this, when you're talking to this one and you say, give me data A from this, it doesn't matter if it's underneath or not. The Java programmer doesn't care, right? The data's over here. That's fine. It's ready for transfer. Just pick the block up and send it away.
And
So,
how can the other part recover the information if there's no either?
I'm sorry?
How can the other part recover the information if there's no either?
How can the, I'm not sure.
You transfer all the bits over the wire.
How do you deserialize it?
Yeah.
I don't perceive that as a problem.
You know that you're
Yeah, sorry, you get the data back, right, over the wire. Sorry, okay, that's a good answer. Thanks, Brian. So this ends up back on the remote heap, if you will, right? And then, and then just create new, synthetic headers, or we call them derived, but just create new ones to point back into it. Right, you know the size, the constant. Now, if you start to mix the data and so on, you're going to need some sort of scheme for that. I agree, but in this particular case, right, there's no copying in terms of accessing the data from the Java heap and so on. Very, very easy, simple. You can express it simply. All these things are just very natural occurrences. And so thanks for sitting through this, folks, because that's all I've got.
I have a suggestion for your last use case.
Sure.
An object which serves as a replacement, and you need a place to new operator of some sort, so that you can basically fire up a buffer and then allocate in sequence any number of packed objects into that buffer, and then close it off, and then you have your contiguous memory.
Sure.
That would be a way that would play nicely with the Java garbage collection, because at all times there would be sort of a known containing object that would contain everything that you're building.
Yeah. Okay, we can talk about that. I'm not certain I.
Is that not like buffers are?
So that's what I was going to say. That feels a lot like byte buffers. So I maybe want to get clarification on your example, because that's exactly what I'm trying to avoid here. So I'm over time. Alex, do you want me to? I'm cutting into your time, Charles. Your call.
Same topic.
Just done better. Let's see. So I guess for the rest of it, I'll give Charlie. I almost did it. I'll give Charlie his time. But thank you. If you have questions, please come beat me later. It's fine. Thanks.